Hello everyone, welcome to IIT-JAM in Chemistry tutorial number 29, and this is the lecture number 7 of the physical chemistry chapter liquid state. In this 7th lecture of the chapter liquid state, we are going to discuss the next subtopic of this chapter, viscosity of liquid, and this is the first lecture on this subtopic where we are going to discuss viscosity, fluidity and coefficient of viscosity. Let's start with the term viscosity. First, let's define this. So the resistance to flow exhibited by a fluid, or this fluid may be liquid or gas, this is known as viscosity. Suppose some liquid or gas is moving from left to right or to the backward to forward direction, then in the opposite direction there is a frictional force or a dragging force which resists that liquid or gas to flow in the forward direction, and that resistance is called viscosity. And this is mathematically expressed by the term viscosity coefficient or coefficient of viscosity, and it is denoted as eta. Eta is defined as the dragging force per unit area required to maintain unit velocity. And what is the dimension of eta? The dimension of eta, that is coefficient of viscosity, is pressure into time. So its unit must be Pascal second, or in the CGS convention it must be dyne per centimeter square into second. Now the next term comes fluidity. What is the definition of fluidity? Now the definition of fluidity is, this is nothing but the reciprocal of viscosity coefficient eta. That means mathematically we can express fluidity, that means phi, which is equal to 1 by eta. Now if you have two liquid mixtures, the liquids must be non-polar and non-associating liquids. In that case they are present by the amount of their mole fraction x1 and x2, so that x1 plus x2 equals to 1. Then their combined fluidity phi must be following this equation number 11, which is log phi equals to x1 log phi 1 plus x2 log phi 2. Next, let's move on to the mathematical derivation of eta. This is a liquid which is flowing through this pipe, and these lines are indicating the flow of that fluid. It may be liquid or maybe sometimes gas. Now this is the center of this cylindrical pipe, and along this perpendicular line of the cross-section area of this pipe, in the perpendicular direction, the velocity of the liquid is highest, because the liquid molecules during their movement have to overcome the intermolecular attraction forces, and this is playing the role of the dragging force which they have to overcome, and this dragging force is in its own terminology known as viscosity of the liquid. Now we have to mathematically give it in the form of an equation as viscosity coefficient eta. So how we shall derive this eta? So if these lines are considered to be different layers, cylindrical layers, then this arrow and this arrow are the same layer, so they may be termed as the lower layer. Then the next layer, this one and this one, are the upper layer. So I am just taking the bottom part. This is the lower layer, upper layer. If this is the lower layer, this is the upper layer. If this is the lower layer, this is the upper layer. If this is the lower layer, this is the upper layer. So along the central line it has the highest velocity. So these are two layers. This is the lower layer with surface area A, and this is the upper layer with the same surface area A again, and both the layers therefore have the same surface area. And this is the lower layer with velocity u1, and this is the upper layer with velocity u2, so that u2 is greater than u1, and their vertical distance is y. And the force now experienced by this layer, this upper layer, is experiencing some dragging force which is caused due to this layer. And since this layer is moving in this direction and the driving force is in the opposite direction, therefore it is getting the negative sign. and this dragging force F minus F is directly proportional to the area of the surface of the layer, and also it is directly proportional to the difference between the velocity of the two layers, and it is inversely proportional to their vertical distance. And the combined form of this proportionality relationships is minus F is proportional to U2 minus E1 over Y into A. Now if these two layers are very much close to each other, then in that case, for these two adjacent layers, Y may be written as dy because Y becomes very small. This U2 minus E1 can also be written as du because this difference also becoming very small. Thus, the previous proportionality relationship can get the form: in place of U2 minus E1 we're writing here du, and in place of Y we're writing here dy. Therefore minus F is proportional to du dy into A, and here we give some proportionality constant eta, and this eta is the proportionality constant which is nothing but known as the viscosity coefficient. So eta, thus we get the derivation of eta. So eta is minus F dy du divided by A. That is, this if we rearrange this equation number 12, then we get the form of the expression of eta. And from here we can also get the dimension and unit of eta. Look at this slide, the previous slide, where we have defined viscosity. The dimension and unit of eta already had been mentioned. So eta has the dimension of pressure into time, that is Pascal into second, or dyne per centimeter squared into second. Remember this slide? Okay, so this part. And here, according to equation number 12, we can derive this form. So eta equals to minus F by A dy du. So F is force, A is area, dy is distance, du is velocity. So let's put the dimensional forms. Okay, force by area means pressure, distance by velocity, velocity means distance by time, that is pressure into time. So Pascal second in the SI unit, and dyne per centimeter square is the unit of pressure in the CGS unit. So dyne per centimeter square into second. Okay, so these two are the units of viscosity coefficient. Now the dimension and unit of in the SI symbol, dimension unit of eta in the SI symbol, the force is having the symbols ml to the power minus 2, area L squared, distance L, and velocity L into T inverse. That means mass length per time squared, area length squared, distance length, velocity length by time. So the final form in the SI dimension, in the SI symbols, it is mass per length per time. So Pascal second is nothing but having the dimension mass per length per time. So the corresponding unit in place of mass is kg, in place of length it is meter, and in place of time it should be second. So kg per meter per second in the SI unit, or in the CGS unit it must be gram per centimeter per second. Now move on to the question: which of the following is not the unit of viscosity coefficient? So here are four options here. Okay, so kg per meter per second, just we have derived this. Pascal second, this one also have been derived, and this one also have been derived. Okay, these are all the units of coefficient of viscosity, but kg per meter into second, no, it doesn't match with the dimension of pressure into time. Therefore option A is the correct answer. And next question, the SI unit of fluidity. Fluidity is the reciprocal of viscosity coefficient. Therefore it should have the inverse dimension in the inverse form of viscosity. That means if the SI unit of viscosity is Pascal second, that is Newton per meter square into second, then the unit of fluidity must be its negative power. Okay, that means it is Newton per meter square per second whole to the power minus 1. So it becomes meter square per Newton per second. Therefore it matches with this option. So option B is the correct answer. So that's all for the first part. Thank you. Have a nice day.